So for my project, I decided to do analysis of variance, or more commonly known as ANOVA. Before you can actually talk about the ANOVA, you have to start with either an experiment or a study. And in this experiment or study, you have to have at least one factor or independent variable that you are manipulating in the study. And this factor has to have at least two levels, so that you have at least two groups that you can compare in the ultimate when you finish your experiment. And then you also have to have at least one response variable, or you can have one response variable that you're testing to see if the outcome of this experiment is significant or not. And then your ultimate question that you're asking is, does this factor actually affect your response variable? And here's an example experiment. There's an experiment that was conducted to investigate whether diet affects coagulation rate in rabbits. And for this experiment, there was two diets that they were comparing. They were comparing diet A and diet B, and there were only 4 rabbits for this experiment, so they put 2 in each rabbit or each diet. And for this experiment, the factor is the diet, and it has 2 levels, A and B, and the response variable is the coagulation rate of the rabbits. So you're trying to see if the factor will affect the coagulation rate. So they're using A and B to compare them. Then what is the ANOVA actually used for? Well, the ANOVA is a statistical procedure in which you are testing to see if the means of 2 or more groups are statistically significantly different. To test this, you have 2 hypotheses that you will start with. The first is the null hypothesis, where you are assuming that there are no differences between your 2 means of your groups, or 2 or more groups. And then you also have the alternative hypotheses, where you would have significant differences between your groups. Your goal is ultimately to reject the null because you want to see that there actually is a significant difference in your groups. So then your factor would be affecting your response variable. And how do we evaluate using the ANOVA? You start by creating an ANOVA table, which consists of 4 components, as you can see from the picture. There's a column for the sum of squares, the degrees of freedom, the mean squares, and the S statistic. And the table is important as each piece works together in your analyses at the end. So first I'll talk about the sum of squares. The sum of squares is basically just the sum of all the differences for each observed value from the mean, and then you square them and you add it together, and there's your sum of squares. For the total sum of squares, you take the amount of error, assuming that the factor has no effect. So you would take the mean of all the scores at once and take the difference from each score from the overall mean. So you would ignore the diet in the example that I used. And then for the error sum of squares, you would take the amount of error assuming that the factor has effect. So you would put in the factor again, and you would compare the means for each group instead of overall. And then you also have the treatment sum of squares, which is the reduction of error after assuming that the factor has an effect. So you just take the total sum of squares minus the error sum of squares, and you get the treatment. Next, to talk about the degrees of freedom. It's the number of independent elements in each sum of squares that is allowed to vary. So for the total, you would take all of your observations minus 1, since you were estimating 1 overall mean for the entire group. So you would lose 1 degree of freedom for that. For the degrees of freedom for the error, you would take the total number of observations in your study minus the number of treatments, as you are taking 1 mean for each level of your treatment. And then you have the degrees of freedom for your treatment, which is all of your number of treatments minus 1, as you're estimating another mean just for the treatment. You have the mean of squares. The mean of squares for the error is the estimate of experimental error variance, or the variation within your groups. So the amount of variation between your subjects in your 1 groups. So you try to have less of that. You don't want a lot of variation within your groups. And then your mean square for the treatment is the estimate of experimental error variance plus the variance among treatments, or your variation between groups, so the difference between the means of your groups. And these are found by taking the sum of squares divided by their respective degrees of freedom. Which leads me to the F statistic, which is one of the parts of your ANOVA table that you would use to evaluate whether you had a statistical significance or not. And the F is just a ratio of the mean square for treatment over the mean square for error, which is just the variation between groups over the variation within groups. And you would, if you have a small f, it would support the null hypothesis because you would have a greater effect of the error than the treatment. So that would mean that there isn't as much of a difference between the groups. And if you had a large f, that would support your alternative hypothesis, as there would be a greater variation between the groups than within the groups. which is what you would rather have. You also use the p-value to evaluate whether or not your results are statistically significant. Your p-value is just your probability that your results are due to chance. Ideally, you would want a small p-value, and typically we use less than 0.05, as that would mean then less than 5% of your probability that your results are due to chance alone. And if your p-value is small, you can reject the null and conclude that there are significant differences between your groups. And going back to the example with the coagulation rate in the rabbits, we can see from the p-value on the NOVA table is 0.0513, so it's around the 0.05 value mark for the p-value, so we can conclude that there's marginal evidence that to reject the null and conclude that there is significant factor effect on your response variable, so that the diet does actually affect your coagulation in the rabbits. And then quick few reasons why this is important is it's better than doing multiple t-tests, which is just comparing two means of two groups. This one you can use more than two groups, so you can do one analysis for all of the groups where you can just save time instead of having to do multiple 2x2s. And then it also decreases your chance of getting type 1 error, which is seeing just an effect that actually isn't there. Any questions?